The electrical grid operates on a precise physical law. The moment you flip a light switch, a power plant somewhere must generate that exact amount of energy. Supply and human demand have to match perfectly every single second. When that balance is met, the system enters a steady rhythm. This is the grid's heartbeat, a uniform sine wave pulsing at exactly 50 or 60 hertz. For over a century, keeping that heartbeat steady was a natural byproduct of how we generated power. We relied on the massive, heavy, rotating machines inside coal and nuclear plants. These multi-ton steel turbines spin with immense momentum. If a sudden surge in demand hits the system, that physical weight shrugs off the impact, acting as a natural shock absorber. Engineers call this inertia. Historically, the stability of our entire electrical system wasn't a software calculation. It was a result of raw analog physical weight. But the grid is changing. As we transition to wind and solar, we are moving toward inverter-based resources. Unlike the fossil fuel plants they replace, solar panels and wind turbines don't have those massive, heavy spinning masses directly coupled to the grid. This creates a light grid. Without that physical weight to act as a brake, the frequency can plummet almost instantly during a failure. This is called a high rate of change of frequency, or RoCoF. If the frequency falls too fast, automated relays will cut power to neighborhoods to keep the whole grid from collapsing. By removing the weight of the old generators, we've stripped the grid of its primary defense, leaving it vulnerable to sudden, high-speed failures. Imagine a major power plant suddenly trips offline. In an instant, the grid is missing a massive chunk of its supply. To see how the system survives, we slow time down. Within 50 milliseconds, the frequency line dives toward the danger zone. During these first milliseconds, remaining physical inertia takes the hit, acting as a brake and creating a tiny curve in the line. But on a grid powered mostly by renewables, that physical momentum is exhausted almost immediately. The analog brake fails, and the frequency resumes its plunge. We are now less than a tenth of a second away from a total system collapse. At the 100 millisecond mark, the grid's digital defense activates, Fast Frequency Response, or FFR. FFR is powered by battery energy storage systems. These batteries use high-speed sensors to detect the plunge and prepare an immediate injection of power. Batteries inject a burst of power to catch the falling frequency. This synthetic inertia creates a nadir just above the blackout threshold. With the fall arrested, the frequency begins a slow climb. Traditional regulation systems spool up to push the heartbeat back to center. The speed here is key. FFR stabilizes the entire network in less than the time it takes for a human to blink. It effectively replaces the physical weight of a coal plant with digital code and chemical energy. Back in real time, the lights didn't even flicker. A major crisis was averted in the time it took you to breathe. This marks a shift in how we maintain the split-second stability of the power grid. We are leaving an era of stability managed by heavy iron and shifting toward one managed by high-speed power electronics. This digital shock absorber allows us to remove old fossil fuel plants without making the grid more brittle. While it doesn't solve every challenge of green energy, fast frequency response provides the sub-second stability required to operate a grid that no longer relies on the physical weight of the past.